Hello students, welcome to my lecture series on reinforced concrete structures. In this class, I am going to discuss about design of shear reinforcement. The outcomes of today's lecture are like this. On completion of today's class, we will be able to know shear stress distribution in RCC beams. As we discussed, as we know, what is the shear stress distribution in our homogeneous beam that I already discussed in your strength of material subject. Now we can discuss the shear stress distribution in the RCC beams. And then you should know what is the effect of shear in the beam, and to counteract this shear in the beam, what type of shear reinforcement, what are different types of shear reinforcement we have to provide it, that also you should know. And after that, after knowing all those things, what are the for designing shear reinforcement, what are the IS code recommendations are available as per IS 456-2000, you should know about that also. Right? Now let us recall what are the things we have discussed in last class. In last class we have designed the problems, designed the singly reinforced beam in two different ways. First way of designing the designing the beam is when the characteristic strength of a steel and when the characteristic strength of a concrete is given, and for a given design load you have to calculate what are the dimensions of a beam and what are the amount of tensile reinforcement required. And second type of problem is when the predefined dimensions are there. According to the dimension, what are the amount of steel required for that particular singly reinforced rectangular beam, that we have to calculate in second type of problem. As we know that for determining the dimension of beam, we have to follow various steps, like first we have to assume that overall depth, then from the overall depth we have to calculate what is that width of the beam. When we know the overall depth, from that also we can calculate what is the effective depth when the effective cover is known to you. Then we have to calculate the load, what is the total load acting on that, that is the sum of the live load and the dead load, and that should be multiplied with a factor of safety. Then we will get the design loads, or you can say factor design load. Based on the design load, we have to calculate the dimension by equating our factor moment of resistance or limiting moment of resistance with respect to the factor bending moment. That factor bending moment will be calculated with respect to the factor load what we design for that, and this bending moment equation depends upon the for what type of beam we are designing. If you are designing for a simply supported beam carrying a UDL throughout, then that factor bending moment would be WL square by 8, that equal to that WL square by must be equal to your limiting moment of resistance. Limiting moment of resistance can be calculated by using the formulas which are available in the code corresponding to their grade of concrete, grade of steel. That is, say for Fe415, that is 0.138 FCK into BD square. Equate these two. From that we can calculate what is the D value is. Here the D is for given bending moment or a factored bending moment, what will be the required depth. Then we have to compare required depth and already assumed depth. If the required depth is less than that assumed one, so we can go proceed with the assumed depth and we go for the next steps. And then we go for checks. Say we have to apply the check after calculating area of tension steel, and we have to go for minimum area of tension steel provided, a maximum area of tension reinforcement provided. For that we have to check with that with respect to the codal provisions. Then second part, just he will give the dimensions like B and D. They are predefined, and so according to that we have to calculate what the area of steel is. The area of steel calculated, first we have to decide what type of section it is, whether it is the under reinforced section or the over reinforced section. So in this type of problems, he will give dimension, along with the dimension he will give the bending moment. With respect to the bending moment, we have to calculate what is the factor bending moment is, and for given grade of steel, and we have to calculate what is the limiting moment of resistance is. By equating a factored bending moment and limiting moment of resistance, we can decide whether MU is less than MU limit, then we can say it is under reinforced section. MU is equal to MU limit, I can say it is a balanced section. If MU is greater than MU limit, then we can say over reinforced section. So if you get the under reinforced section according to those rules, then for the under reinforced section we have to calculate the steel corresponding to the tension zone, that is a moment of resistance corresponding with moment. We have to calculate with respect to the moment of resistance formula in tension zone, that is Mu is equal to 0.87 Fy AST into D minus Fyast by Fck into Bd. If you substitute all the parameter in this equation, we will be getting Ast in the term of quadratic equation. If you solve that quadratic equation, we will be getting what is the AST is. That is area of steel provided. That value you have to check with the minimum area of steel provided and maximum area of steel we can provide it according to the codal provisions. So those are the things we have elaborately explained, and we have designed some problems, some beams also from the given data. So this is all the story of your beam design. So that is we have designed with respect to the bending moment, and we are considering the things that limit state of collapse in flexure condition. Then another condition we have, that is limit state of collapse in shear. What is that? Limit state of collapse in shear. So if you apply a load on any deformable body, that body may deform into various fashions, like it may bend, it may shear off, or it may twist, or torsion may apply, or this body may compress. So what we did in our first part, that is limit state of collapse in flexure condition, we have considered only bending of the beam, and we have designed that particular beam. Now we will consider one more parameter, that is shear. If load is acting on a beam, mostly beam will bend and shear off first, right? Then we are bending part of that we had already discussed. With respect to that, we have designed the beams in our previous lectures. In this lecture, we have to design a beam with respect to this shear. Now in this class, we will discuss what is this shear, how it happens, and how to arrest this shear. Those things we have to discuss in this today's class. Say a beam is loaded with a transverse load, is subjected to shear force and bending moments. Right, as I said that a deformable body may, when apply a load, it may deform in any shape. Majorly, it will deform with respect to bending and shear force. We know, based on the concepts of your strength of materials, the rate of change of bending moment is equal to shear force. So when you apply the load, there may be a chance of occurring shear forces. These shear forces will result shear stress across the section, right? And along with the shear force, there may be a bending moment also occurs. That bending moment results in the beam that bending stresses. Now combination of this shear stress and bending stress will will produce a principal stresses which cause the diagonal tension in the beam section. So that is ultimately what is happening in the beam. Because of this principal stresses, these principal stresses are occur due to application of external load. Because of that, diagonal tension in the beam section is happening. This this diagonal tension will do in the beam. This diagonal tension, tensile stresses, causes the failure of the section by producing the cracks. They will produce the diagonal tensile stresses will produce cracks in the beam in the diagonal with 45 degrees with the axis of the beam. That's why I call it the diagonal tensile stress, right? And this crack should be restricted by providing some reinforcement. So we are restricting that shear means, so we have to provide shear reinforcement. The cracks which are happening or which are developed due to these tensile stresses in the diagonal direction, that should be restricted by providing shear reinforcement. So this thing, how to provide the shear reinforcement in this beam, in singly reinforced rectangular beam, those things we'll discuss in this, and what are the codal provisions are there for this, we'll discuss in this class today, right? So how the shear stress taking place in the beam, and how will be their shear stress distributions. So generally we have two types of beams. One is homogeneous beams and heterogeneous beams. You know, homogeneous means they are made up of a same material. Say here for the homogeneous beam, I will consider this beam is made up of only concrete. So this is the stress distribution was studied with respect to the elastic theory. So the shear stress in particular beam, that is homogeneous beams, can be calculated by using this formula, that is tau equal to V into Ay by I into B. So this formula is not new to you. This formula already you might have studied in your strength of material subject when you are discussing about shear stress distribution across the rectangular section or I section or circular section and triangular section. There it is a common formula. This formula can be used for any type of section. This formula can be modified corresponding to the respective section. So for this formula, by using this formula, we can calculate what is the shear stress distribution is. So here I am considering a homogeneous rectangular beam. For that, the data corresponding to this homogeneous rectangular beam, if I substitute here, I can find out what is the shear stress in that particular beam is. Again, the shear stress in this particular beam can be calculated by shear force. Here V is nothing but shear force multiplied by A into Y. A into Y is the first moment area of a section about the neutral axis, and here I is nothing but moment of inertia of a beam section. B is width of the beam. If you substitute all those values in this equation, we will get what is the shear stress in that particular homogeneous beam. But here the shear stress distribution for this homogeneous beams it is a parabolic in nature. It is parabolic in nature. That means at zero shear stress is zero at the top fibers and bottom fibers, and it will be maximum at a level of neutral axis. So this tau max, that is maximum shear stress, can be calculated by using that formula. This maximum shear stress is 3/2 of average shear stress. That is 3/2 can be written as 1.5. So tau max equal to 1.5 into V by BD. Here V is the average shear stress and BD is the dimension of a cross-sectional beam. This is how we can calculate the tau max in the homogeneous rectangular beam. Next we have a heterogeneous beam, that is a RCC beam. I am considering a RCC beam as a heterogeneous beam. Why? Because it is made up of two different materials. One is concrete, another is steel. That's why I can call it as a heterogeneous material. Right? According to that elastic theory, what we define with that our homogeneous beam, a very difficult phenomena that for calculating that maximum shear stress in that RCC beams. But if you observe this, the shear stress varies in this RCC beam parabolically with 0 at the top and top compression phase. This is a top compression phase, and maximum at the neutral axis, and constant from a neutral axis to the center of gravity of the steel. Right? So here in this zone, why it is constant means we are not considering concrete here. Here we have another material called steel. Though we have the concrete below the neutral axis, there is a tension zone. That concrete will consider as a crocked concrete, that is, I can say, useless concrete. I have to explain you that why we should be use the concrete in this tension zone. To only purpose of use of concrete in tension zone is to hold the reinforcement in position, or to form a bond with the steel reinforcement. That is the purpose why we are providing concrete in tension zone, because the tensile forces are taken care by only the steel reinforcement, none by concrete. Already we have discussed in our previous lectures. Right? So I am again explaining here. It will. So I think you got the difference between the shear stress distribution of a homogeneous beam and RCC beam. That is completely parabolic in homogeneous case, and here it is parabolic up to a neutral axis, and then it will be a constant. Then how to calculate this tau max? According to this, the tau max can be calculated by V by Bz. That is, V is the shear force, and B is the width of the beam, Z is nothing but lever arm. Lever arm is nothing but it is a distance between line of action of forces which are acting compression zone and tension zone. So it is a parabolic portion. Here we have a compressive force. It is a rectangular portion. Here we have a tensile force. The distance between these two forces are called a lever arm. Right? But it is a complex phenomena. But to overcome this problem, our code has given one recommendation that as per IS 456-2000, it will be that nominal shear stress or average shear stress can be calculated based on that VU by BD formula. That means here IS code is considered that this TV means a nominal shear stress or the average shear stress will be considered as like this. So from here to here it will start and up to it will form a rectangular distribution. We are considering here a rectangular distribution, and here call it as a average shear stress. Why we are calculating assuming it as an average shear stress means if we check here in parabolic position, here the shear stress at this level is up to here, at this level is up to here, at this level is up to here, at this level is up to here. If we average, if we do the average of all these shear forces, and if you plot that, you will get a in the form of rectangular shape like this. So this portion of shear stress is called a tau v. Tau v nothing but nominal shear stress or a average shear stress. This assumption is given by our IS 456 2000. We are not considering the first case, that is homogeneous case. We are not considering the shape in the second case, that is heterogeneous case. But code has given for simplicity of calculation, that is, it is assumed as a rectangular distribution. The rectangular distribution, that is that the shear stress will be given in this rectangular distribution of shear stress is average shear stress, or I can call it as a nominal shear stress. That average or nominal shear stress can be calculated by using this formula, that is VU by BD. Here VU nothing but ultimate shear force, I can say factored shear force, and B is the width of the beam and D is the depth of the beam. So what do you mean by this ultimate shear force? That means the shear force should be multiplied with a suitable partial factor of safety. That the shear force is called ultimate shear force. Generally, we can use that a factor of safety in limit state of collapse in shear condition, that is 1.5 for shear force. Right. Now we can see the effect of shear here. So as I said, we are providing the reinforcement to counteract the shear effect. Now we'll observe how this shear effect will be in a particular beam. To analyze this effect of shear in a particular beam, here I am choosing a simply supported beam carrying a UDL throughout. And I have divided this beam into two zones. This dotted line will be showing that is neutral axis of the beam. Above the neutral axis is a compression zone, and below the neutral axis it is a tension zone. In the tension zone of the beam, I have considered three elemental parts in a beam, that is namely 1, 2, 3. The elemental part in a tension zone of a beam, a part 1 is considered somewhere between midspan of the beam and the support of the beam. And second element of the beam in the tension zone is considered exactly at the middle of the beam, or I can say just near to the middle of the beam. And third portion of element will be considered at or near the support. As we know that when a simply supported beam subjected to UDL throughout, we will get a maximum bending moment at the center of the beam and zero bending moment at the support of the beams. And we know that from the end condition of the simply supported beam, we will get the maximum bending moment at the midspan. When the bending moment is maximum at that particular situation, our shear force will become zero. I can say here the maximum bending moment, there is no shear force at this mid of the beam. And similarly, if you come in the other end condition at the support, here at the support the bending moment is zero and shear force will be maximum. Right? With this knowledge and with this data, we will analyze these elements of a beam one by one. So let me consider first element of the beam, which is chosen at the tension zone. Where it is located? It is located in between somewhere mid of the beam and the support of the beam. As here, see, it is zero shear force, here maximum shear force, zero bending moment, maximum bending moment. As we are considering this element here, that means we will get some value for bending moment and we will get some value for the shear force at this particular section. So here the bending stresses are exist at the section and shear stresses also exist at particular that section. So these are the shear stresses which are acting at the section of the that elemental part in tension zone, and these are the bending stresses. This is denoted with a sigma, and shear stresses are denoted with a tau here. Now next consider second element which are situated in tension zone here. And as per this diagram, as considered beam, your second part will be at the mid of the beam. So as we know from the boundary condition of the beam, at the mid of the beam, the bending moment will be maximum and shear force is equal to 0. That means I can say your element 2 is only subjected to bending stresses, and those bending stresses are in the form of tension. That means as you are choosing the element in tension, so it is called a bending stress with respect to the tension. Suppose you are choosing that element in compression zone, there also we get one more stress, that is bending stress, but that bending stress is with respect to the compression. But we have chosen that that element in the tension zone, so that's why that stress induced in this particular element is bending tensile stress only. So what will do this bending tensile stress in this particular element of the beam? It will try to split this element into a parts. So this part of the element will move in this direction, this part of the beam element will move in this direction. So because of that tensile stresses, there may be a chance of a crack, or there should be a crack occurs. So this crack will be definitely a vertical, because same amount of forces are acting. This bending tensile stress is acting in this direction, the bending tensile stress occurs in this direction. So these two stresses are try to split or try to pull this element in two different parts. So the cracks appears in the middle of this element will be vertical. I can say this is a 90 degrees cracks. Right. Now coming to your third element. This third element was considered at or near to the support. As per boundary condition of the simply supported beam, at the support the bending moment is equal to 0 and shear force will be maximum. So due to this stress condition, here if you observe in this element, here I represented with a ILJK. Because of only shear stress or shear force acting on that beam, this I and K try to move away from each other. That means there will be a tensile force induced because of shear force. Due to shear force, pure shear force, at the corners of this element, small element, there will be a what? At I and K, the tensile forces are acting. The stresses induced due to these tensile forces are called tensile stresses. These tensile stresses are try to drag these two corner of element in this fashion. So it is the initial position of that element, and after application of pure shear here, your tensile forces are developed, and due to that tensile stresses are occur. Due to that tensile stresses, this element will take a shape of this rhombus like this here. That means this tensile stress try to pull this part in this direction, and this tensile stress in this direction try to pull here. So because of this two pulling nature, there may be a crack appear here, that is in the direction of diagonal of this elemental part. So I can say because of this diagonal cracks are occur. The inclination of this diagonal crack with respect to the horizontal is 45 degrees. So due to this condition of stress, the diagonal IK of the element is subjected to tensile stress. Already explained that. As concrete is very weak in tension, so it is split along the diagonal and develops a 45 degrees. Though the concrete is strong or it has a more shear strength, but because of the shear force, there is a tensile forces are developed. Due to the tensile force, tensile stresses are developed. So concrete is very weak in tension. That's why it is splitting into two parts and forming a diagonal crack for this particular element of a beam. Right? The cracks are the diagonal. What is the tension which is caused in the tension zone of a beam due to only shear at or near to the support is called a diagonal tension. and this diagonal tension will cause a 45 degrees cracks. As we know that concrete is quite strong in shear, but diagonal tension occurs due to the tensile forces. Diagonal tension occurs due to the tensile forces, which is due to the shear force. So it cannot be restricted, the shear cannot be restricted concrete alone. That's why to restrict the shear cracks, we should provide the shear reinforcement in the beam. So these are the final conclusions of our analysis of three different elements in the tension zone of a beam, right? So let me conclude first one. At or near the midspan, the cracks are vertical. You know that these are the crack at the mid of the span. This is appear like this. It is a 90 degrees crack. This crack will happen only because of what? Bending or flexural crack, you can say, because there is no shear force acting on the center of the beam, so it is only bending. That's why flexural cracks are occurs. Now second conclusion I can draw from this analysis is, at or near the support, cracks are inclined at 45 degrees. Why it is inclined at 45 degrees? Here diagonal tension will occur and the tensile force try to drag in this direction, there may be a diagonal cracks. The inclination of that crack will be 45 degrees with respect to this horizontal. So this is due to only shear. That's why I can call this diagonal cracks also called a shear cracks. So these are in the form of this. Now I have chosen one more element that is in between midspan and then the support. Their condition that the cracks are vary between the inclination of 45 degrees to 90. So this 1, 2, 3, these three cracks are in between mid of the beam and the support, in between support of the beam. So the inclination of those cracks are 45 degrees to the 90 degrees. Here both may happen. This is because of flexure or because of shear. That's why these cracks will happen due to flexure as well as shear. So these are the conclusion I have drawn. So these conclusions are very important for your competitive examinations. So a question may ask like that: at the mid of the beam, the cracks appear due to what? Shear, bending, or shear and bending? None of the above. The crack is exactly vertical. That is due to only bending. So where the answer will be only because of bending, that mid of the span the crack will be vertical, right? So to counteract that shear deformation or shear stresses developed in the beam, we have to provide shear reinforcement. That we have different forms of shear reinforcement, or we can say different types of shear reinforcement. That is vertical in the form we can provide in the form of vertical stirrup, inclined stirrup, and bent up bars. Or this also kind of bent up bars along with vertical stirrups, right? See, let me discuss the first one, that is a vertical stirrup. So you know the stirrups are placed in vertical direction. That's why I call it the vertical stirrups. So stirrup is not a new thing to you. This is a simple new word. That is a steel bar bent into a required shape. That is a stirrup, and that should see the vertical stirrup is vertically placed around the tension reinforcement. That's why we can call it as a vertical stirrup. So in the beam you have a tension reinforcement. Around that we will provide a stirrup. So you may get a doubt that, so it is a singly reinforcement beam. We have a reinforcement in only tension zone. Then how can I make it around that tension reinforcement, and how these stirrups can be held in position? So along with this main reinforcement in tension zone, we will provide a hanger bars in the compression zone. So for the hanger bars, there is no separate design for that. Just will provide hanger bars with a diameter of less than that of the main bars. There is no particular design for that. Just simply will provide in the compression zone to keep that stirrups in position. And the diameter of these stirrups are varying from 6 mm to 16 mm. And free end. So this is a free end. Free end of the stirrups are anchored in compression zone. So this, if suppose, let's say this is a beam, it is above this, it is a neutral axis, above this compression zone, below this a tension zone. In compression zone, this will be the free end. Free end of the stirrups are anchored to the anchor bars in a compression zone. And based on the magnitude of shear force, to be restricted, we have to use different vertical stirrup. That may be a single-legged vertical stirrup, two-legged vertical stirrup, four-legged, and I can say eight-legged, or I can say multi-legged. So as it has only one leg like this, that's why I can call it a single leg. It has a two legs vertical direction, two leg. It has four legs, 1, 2, 3, and 4. So 4 legs. Likewise, we have a many leg. That's why I can call it as a many legged or multi-legged vertical stirrup. They should be used based on the how much they has to how much they depend upon the type of or the based on the magnitude of shear force that should be restricted. Then we have to use the type of vertical stirrups. And we have another type, bent bars along with vertical stirrups. Here we have a longitudinal bars, and these vertical lines will show you vertical stirrups. Here in this type of beams, we will provide a bent up bars and vertical stirrups simultaneously to restrict the shear force. So longitudinal bars of a beam can be bent near the support. This longitudinal bar of the beam will be bent near to the support, as we know that the diagonal cracks will occur at the supports only, at the supports, as the only maximum shear force and bending moment 0. So there is no bending moment here, or the minimum bending moment to be restricted. That's why this portion of a bar will be used for restricting the shear, not for bending moment, because at the support bending moment is 0 and shear is maximum, right? So these bent up bars are provided at the bars will be bent up at the supports, and they restrict the diagonal tensions. There are equal number of bars to be bent on the both side to maintain the symmetry. As this is a beam, it is a here this shows the continuity of the beam. That means we have a beam further, and we are bending here, and other side of the beam also we have to bend in this direction to make it symmetric, to maintain the symmetry of the beam. And the bars should be bent into 45 degrees, and this combination of vertical stirrups and the bent up bars are used to resist where heavier shear forces are there. In those situations, we will use the combination of shear reinforcement. And we have the finally inclined stirrups. These inclined stirrups are generally provided at a angle of 45 degrees, provided over the full length of the beam like this. Right? Then we will discuss IS code recommendation for shear design. First, we have to calculate nominal shear stress. The nominal shear stress is tau c, that can be calculated by using earlier formula, that is factorial shear force by area of cross section beam. So from this formula we can calculate nominal shear. Then we have to calculate design shear strength of a concrete. As we know that the shear strength of the concrete is good in resisting shear forces, so that the shear strength of the concrete consider for design of RCC beams, as compressive tensile strength are not considering for design of RCC beams. And shear strength of RCC will majorly depends upon grade of concrete and percentage of tensile reinforcement. If the grade of concrete increases, that shear strength of the concrete also increases. If increasing the percentage of tensile reinforcement, then also your shear strength of the concrete increases. So based on this concept, we have to define what is the design strength of a concrete, that is tau c. As I said that it depends upon the grade of concrete and the percentage of tensile reinforcement. According to the table number 19 of IS 456-2000, as I said, there is a percentage of tensile reinforcement, it is a grade of steel. For particular percentage of tensile reinforcement and for particular grade of concrete, what is the design shear strength of a concrete, we can calculate. So let example take here, I have a 1% of tensile reinforcement and I am using M25 grade of concrete. What is the design shear strength of that particular grade of particular concrete is? So there is a 1% and correspondingly grade of concrete is M25. So the design shear strength I will be used is 0.64 Newton for mm square. Like that we have to calculate. So if you are getting the percentage of steel in between these two values, then we go for interpolation technique. From that we can calculate what is the design strength of a concrete. And we have to calculate what is the maximum shear stress. Right. In no circumstances, under any circumstances, even you are providing shear reinforcement, the nominal shear stress tau V must be less than tau C max. The tau C max is called maximum shear stress, and this depends upon the grade of concrete. And for the as per IS 456 2000 in table number 20, for different grade of concrete, what is the tau C max is. So this table is very important for your competitive examination. He may directly ask what is the maximum shear stress of a concrete M20 grade. So this table you have to remember for your competitive exam purpose. So otherwise, when you are designing the shear reinforcement for particular beam, you will be eligible for taking your code book to your examination. So for M20 grade of concrete, it will be 2.8 Newton for mm square. For competitive, no other go. For competitive examination, you must remember all those values. Right. And similarly we have the IS code recommendation for minimum shear reinforcement. So how much minimum shear reinforcement we have to provide, and under which situation we have to provide. The minimum shear reinforcement will be provided when your nominal shear stress is less than or average shear stress is less than design shear stress of a concrete. So in this situation, particularly there is no design for shear reinforcement. We have to provide minimum shear reinforcement in accordance with the class number 26.5.1.6 of IS 456 2000 in the form of vertical stirrups. So there is a formula for calculating that is ASV by B into SV must be greater than or equal to 0.4 by 0.87 Fy. According to this formula, we can calculate minimum shear stress required or minimum shear reinforcement provided. So here ASV is the total cross-sectional area of stirrup legs effective in shear, and SV the stirrups spacing along with the length of the member, B is the width of the member, and Fy is the characteristic strength of stirrups reinforcement. In no case it should not be greater than 415 Newton for mm square. And for that maximum spacing of stirrups, we have some recommendations given. For if you are using vertical stirrups, here the spacing must be less of these two. That is the maximum spacing must be less of these two. That is 0.75 D is one criteria. Another is 300 mm. Whichever is less, we have to take as a spacing for the shear reinforcement. If you are using shear reinforcement as vertical stirrups, then we have to consider. The second part is inclined stirrup. That means the inclination of stirrup is 45 degrees. Then maximum spacing should not be greater than minimum of these two we can consider, that is D, that is effective depth of the beam, and 300 mm. Whichever is less, that we consider as our spacing for the inclined stirrups. So that's all for concepts of today's lecture. And based on the today's lecture, we will discuss a numerical problem, that is calculation of nominal shear stress. Say the problem is given that a singly reinforced rectangular beam of 230 mm by 450 mm effective depth is subjected to a shear force of 40 kN under working loads, and calculate the nominal shear stress. Here the shear force is given under working load, but we have to calculate the nominal shear stress corresponding to the factored shear force. That factored shear force is a design shear force. The design shear force can be calculated multiplying with a suitable factor of safety. By using some formula, we can calculate that. Here, given data B is equal to 230 mm, D is equal to 450 mm, shear force given at working load is 40 kN. From this, we have to calculate what the factored shear force is. Vu is equal to 1.5 times 40, that is equal to 60 kilonewtons. The nominal shear stress can be calculated, that is tau V equal to Vu by Bd. Formula we have already discussed, that is Vu is 60 and Bd is 230 into 450. If we calculate that, if we will get the nominal shear stress is equal to 0.58 Newton for mm square. So thank you. That's all for today's lecture.